Okay. Good morning. Before I say anything, turn off your cell phones, please. My name is Tom Leonard. I'm a programmer at Valve. And prior to that, I was lead programmer of the Thief the Dark project at Looking Glass. This morning, I'd like to share my experiences building an AI sensory system. In this sort of GDC way, you start with a big, broad title, and then during the talk, as you develop your talk, it gets a lot more narrow to fit it into an hour. So I'm going to describe a first-person, single-player sensory system. Sorry, I'm totally new to this. I'm describing an approach to designing and implementing a high-fidelity sensory system, although much of what I discuss is probably relevant to other genres. The techniques I describe are based on my experience on Thief the Dark project and my subsequent familiarity with the source code of Half-Life. I'll start by exploring the basic concepts of AI sensory systems using Half-Life as an example, and then I'll move on to the more stringent requirements of the stealth gameplay that was presented in Thief. Before we go forward, I want to define what I mean in this talk by senses. Senses, for the most part, are an engineering metaphor. They're a framework for understanding and designing and discussing a certain part of the AI with the whole team when we use the term senses. It's consistent, with other metaphors we use in the game. Having a real creature with eyes and ears moving through a 3D space, it really lends itself well to using this sort of physiological or neurological analogy. And it's readily understood by any member of the team. But there are limits to the analogy. I think that the game design and the engine you're using and the platform you're targeting are really your problem domain and not world simulation per se. So in this talk, I'm not really going to go into a system that tries to simulate senses. I also am not trying to do any sort of computer vision or robotics. This is basically a system that's designed to make an AI seem to the player like he's sensing the world in a way that lives up to the player's expectations of his own experiences in the world. So I would call this an emulation, not a simulation. So for me, the senses are that part of the AI that gathers information about the items that are interesting to the AI in the simulated environment. And I think it's pretty closely tied to the AI's sense of knowledge. And in a first-person shooter game, often there is no distinction between sense and knowledge so far as a given AI is concerned. I think that senses are sort of, when you design them, they're imbued with a game-relevant component where you know the game or genre you're trying to make, and the decisions you make when you build it feed into the structure that you put together. Finally, I think it's perfectly valid for game logic to go directly into your sensory system, even if it's violating some sort of higher level abstraction. And the value of a good sensory system is that I think it allows you to present to your core state machines well-digested data and broad inputs that allows you to keep those core state machines relatively simple while adding complexity that's feeding in from the environment, letting the environment generate behaviors as opposed to trying to code them in the decision machines. Now, in terms of requirements, when I set out to build this system, that the primary requirement is that it's subservient to the game design and that it's efficient in implementation. So much of what I focus on is trying to achieve what the designers wanted out of the game, and yet still run in this game's case, run on a P120 with 60 megs of RAM. It needs only be as complicated as it needs to be entertaining and robust, and no more. Most importantly to me, it needs to be perceivable and understandable by the player. For this reason, I don't really talk about the senses of touch and taste and smell. because these are things that are really hard to provide feedback to the player about what they're doing to the AI. Now, I know that people have tried, and we discussed on Thief and Thief 2 in particular, doing smell, for example. But it's really hard to communicate the player's own sense to himself. And so we decided to back off on that. Now, my first example is that I'm going to use is Half-Life. I think Half-Life's a good example because it's a pretty straightforward sensory system that gets across most of the core ideas for people who've never worked on anything like this before. And being a game that has strong tactical and presentation elements, it's not a completely boneheaded system either. Half-Life presents sight and hearing, a simple system for information management, and it leverages the basic senses into appealing behaviors. Now, the most basic part of a sensory system is to look and listen to the world. Now, unlike normal senses, this is not a passive event where information just comes at you and then you just kind of decide to do something with it. It's typically an active event where you go out and probe the world, looking for things that are interesting to you, and based on rules, decide if you want to find out more about them and then sort of squirrel away the information. Furthermore, you try to leverage your game design to limit the amount of information or the amount of work you try to do. Now, this doesn't mean it can't be event-driven, and sound systems often are. But even in the case of a sound system, someone has probably culled or qualified the information before it arrives into the AI's event queue or provided some sort of semantics. So I know no one can read this, and I don't expect you to. This is the core, in pseudocode, the core sensory code of Half-Life. And I'm just going to step through it and then discuss some of the ideas that are presented there. So if I'm close to the player, then I begin looking around for anything. So I gather a list of objects and entities that are within a specified distance. And for each one that I find, if I want to look at them, and they're in my view cone, and if I can raycast from my eyes to their eyes, and if they're the player, or if they're the player, so I'm sort of indented there, it's hard to see the indentation in the slide. If they're the player, and I've been told not to see the player until he has seen me, then I move on to the next entity. Otherwise, I set various signals that will be picked up later, depending on my relationship to that entity. And I move on to listening. And when I listen, in this case, I have, just as in Thief, there's a queue of sounds. For each one that's playing, if the sound is carrying to my ears, I add the sound to a list of heard sounds. And if the sound's a real sound, I set more flags indicating that I heard something. But if the sound is a smell pseudo-sound, I set a signal indicating that I smelled something. And then I'm done. I move on to the next entity. So I have a few observations about this block of code. The first thing is that it has a close relationship to the purpose in the game of the thing that it's targeting, and the properties of the AI, and the relation of that AI to the senses. And probably more importantly, it really knows what the relevance of the thing being sensed is to what the player is going through. Furthermore, it has optimizations. The senses are basically limited to things that can actually affect the player, things that later on are going to get fearful or angry or friendly with the player. And things that are indifferent to the player most likely are not even trying to sense the player. Okay, so vision obviously is one of the primary things you're going to find in any game. Vision, in this case, and probably in most cases, is defined as a view distance, a view cone or a field of view, line of sight, and an eye position. Now, in Half-Life, the codes are 2D, so they're infinitely high. When the AI believes something is in the view cone, it casts a ray, and if the ray is unobstructed, that means the object is seen. So we saw that the operations were ordered from least to most expensive, and that's a pretty common pattern. I'm sure most of you used before. The one thing that might have been a surprise for some people is that the vision is, in this case, a game of peekaboo, where the raycast went from eye to eye. And this is because in a first-person game, your sense of your own body is very weak as a player, and the player that it feels like he's seen when he hasn't seen his opponent often feels cheated or doesn't understand why that's happened. So this gets around that problem. This is probably less relevant for other camera, like a third-person camera mode, but there might be something analogous, although that's not a domain that I'm familiar with. The other nice thing in this code is that it's controlling the senses for the enjoyment of the player. The code we saw there was if they're the player, and I've been told not to see the player until he sees me, then I don't see him. And this is basically a small change to a lower-level system that tries to express this high-level goal in the simplest way possible. In this case, this was used in Half-Life to achieve that effect of the head crab jumping out of the darkness at you when you happen to turn to look down like a little hallway, and other sorts of scripting events. The designers just said they wanted this effect, and the AI took care of it without any kind of scripting or triggers. Now, sound is much simpler in Vision, and this is primarily because sound can rely on existing infrastructure inside a game engine, which usually has cues for sound and understands the position of sound and usually has some sort of semantic tags associated with sound. And so the primary job of the AI is determining that something was heard to it and then seeing if the sound was relevant, assigning some sort of AI-specific meaning to it. There's also something interesting in there, which was that the sound system is being used as a catch-all for all positional events where there might be something that there isn't an entity in the world related to it. We saw the example of if a sound was a pseudo-sound, a smell pseudo-sound. And what's happening there is that this is a sound in the world that the player doesn't hear, but the AI does, and is interpreted as a smell. So that's how Barney can comment to you when you're sitting around idly and he wants to comment on the smell of the dead bodies around you. It's also used for the grenade case in with the grunts in Half-Life. So when you throw out a grenade, the point where it lands, a sound that you can't hear is placed in the world, and the AIs hear it, and it communicates to them using going through the same pipeline that there's danger there. Let's all run for cover. And so it's a really useful tool for doing all sorts of things like that. Okay. So I'd like to move on to Thief, because Half-Life is a game that I've sort of learned after the fact and isn't the game that I'm associated with. Now, if you're not familiar with Thief, Thief is a stealth game where the player is encouraged to move carefully through a space with pools of light and dark, areas that are noisy and not noisy, and basically avoid conflict, if possible, completely. In Thief, the penalty for disturbing the environment, there's a penalty for disturbing the environment, which is an important point we'll come to later, that if you alter the environment, the AIs are meant to notice that this has happened. Furthermore, a very important point is that the cost of discovery in Thief was very high. You were not a good fighter, and the odds are you're going to get your butt kicked, or you're going to have to hightail it out, and your plans will be ruined if you are detected. So in this case, the senses of the AI, and really the senses of the player, are the focus of the gameplay. The game is sort of about the ebb and flow of the AI's knowledge in the level, knowledge of you, of your presence. As you're moving through what you see as light and dark to your eyes, the AI, it's like moving through the sort of figurative dark areas of their knowledge. And in this game, it's the senses that provided that. And the core concepts that in this system are going to be very similar to Half-Life. So what I go through will really just extend what we've already covered. Okay, so given that sort of high picture of the game design, I want to talk a little bit about the requirements before going into what the solution was or is. The first requirement was that the system work in a space of a wide spectrum of tunable states. On the superficially, stealth gameplay is is kind of about fictional themes of hiding and skulking and surprising people and getting up behind them and knocking them out, or in certain games cutting their throat or whatever it is. But for the purposes of the senses, part of the real fun is taking the gray zone of safety and danger that typically in a first-person shooter is razor thin, and broadening out that area of uncertainty, and then trying to keep the player on the edge of safety or danger, so that when they break through, they either feel the tremendous relief of being safe or the aw shucks of being caught, and all the while, keeping their heart pounding because they're not sure exactly which way it's going to go. So the important thing about that is that this is a system that can't polarize quickly to the extremes of you being sensed or unsensed, or the player being safe and unsafe. The other thing to note is that the system needs to operate on many more objects than is typical of a first-person shooter sensory system. During the game, because the AIs needed to notice what you had done, and furthermore because the levels involved patrolling AIs that needed to continue patrolling whether they were near you or not, the system needed to basically keep running and be sensing many, many more objects, even when the player was nowhere nearby. For example, you could hide bodies that you had of people you had knocked out or killed, or you could leave blood behind and forget to wash it off the floor. They needed to notice this as they moved through the level, and this presented an interesting performance challenge. Finally, the system needs to be stable and intelligible. The idea is to try to give the player the feeling of an analog system, but kind of avoid the unfun feedback that sometimes you wrestle with in an analog system. Furthermore, the players and the designers needed to understand all the inputs and understand the outputs and have the outputs match their learned expectations as they developed the game and as they played the game. And so the solution primarily is to provide a limited number of player perceivable inputs and then produce discrete valued outputs, sort of enums, not floats. The system here is very similar to Half-Life. There's a view cone and raycast-based vision. There's a simple hearing system that leverages the core sound system that we built for Thief. And we put in game hooks to optimize, to express game mechanics, and to introduce pseudosensory data, like the grenade or the smell. And like Half-Life, the sense gathering is decoupled from the decision process, which I think is a useful thing to note. So Half-Life is basically like sensing is a function that runs. It generates some flags that are transient, that are used only during that frame, and then it's stateless from that, just the next frame you just start all over again. The system here is object-oriented with independently scaled or scalable components. Things were basically scaled based on the relevance of the thing being sensed to the game design, the imminence of that thing having the AI or the thing being sensed having an impact on the player. So imminence is sort of like proximity. And it's also influenced by the state of the AI, whether he's in combat or not. The system is stateful from frame to frame. The idea here is both for efficiency purposes and also to establish a sense of continuity in the senses. It outputs, and this is probably obvious, non-binary outputs. It's not just seen, unseen, what have you. Furthermore, in Thief, we allotted much more time to the senses than is probably typical of a first-person shooter because of its importance to the game design. So here's a scary class diagram of the system. The important things to notice up here are alertness and view cones, sense links, awareness, and visibility. The AI selects a view cone based on the relative position of the player or the observed object. And given that view cone, it combines it with a visibility value calculated for that object. and generates an awareness value. That awareness generates a sense link, which is used later by the AI to generate an alertness value for the AI, or an agitation value. So I'll go into some of these in some detail. The core idea in the system is awareness. Awareness is a range of discrete states that describe the AI's certainty of the presence, the location, or the identity, and the identity of a given object. And although internally it uses some floating point stuff, it's primarily a qualitative value and it's the only thing that's exposed to designers or to other systems. Although it's not strictly part of the sensory system, I should note that the alertness is a big part of this. Alertness in the AI of Thief is the agitation level is directly and very simply derived out of the awareness that it has of the highest awareness it has of any object in the world. And that, in turn, feeds back into the sensory system. The AI stores information in a structure known as a sense link. A sense link is a relation to either an entity in the game or a position in space. And it stores all the relevant information that's exposed to other systems and to the designer scripting systems. The awareness level, the time of the sensing, the position of the sensing, whether there was line of sight, a bunch of other little flags that picked up along the way. It also stores hidden data that's basically data cached from frame to frame to achieve the sort of performance goals that the system needs and to establish continuity. So this is an example that we'll be returning to through the talk. As you can see, I am not an artist. So in this situation, we have a variety of AIs, each of whom has sense links to various things in the world. The one I want to talk about right now is the simplest case. This AI has direct line of sight to the player. The player is in full view in the bright background of my slide, and is absolutely visible to the player. So therefore, to the AI rather. So therefore, this AI has a high quality, first-hand sense link to the player. Sense links in this system are akin to memory or knowledge, and because they're thought of this way, they can be transmitted between AIs through verbalization and observation of the world. They can also be manipulated by game logic and scripts in order to achieve effects that the core AI doesn't support. So here in this case, we have the second AI who's with his companion. In this case, in this scenario, I presume that the first AI has announced the presence of the player. He said, "There he is." And as such, although the second AI does not have a line of sight to the player, he does in fact have a specific high awareness knowledge sense link to the player, which has been tagged as second hand, and that second hand is used later by the higher level AI to generate different behaviors. Now, if this AI, the first AI, had not announced the player but merely run into combat screaming, the second AI would most likely have a sense link to a position in space at or near the player that would have been of probably high awareness, but of much less certainty. It would not be considered first or second-hand knowledge. So for each entity in the game, there exists a visibility property which is independent of any viewer. Visibility consists of lighting, movement, and exposure, plus an aggregation of all three using a formula. Now, by exposure, I mean the size of the object, its separation from other things in space, and its stance. So if I'm close to the wall and crouching down, my visibility is low. But if I'm out in the middle of the room and standing up, then my visibility is high. Based on the importance of the item in the system, the frequency and the resolution of this value is scaled according to what's being calculated, and this is shared amongst all AIs in the system. This is not a per AI calculation. Also, this visibility is an analog value, as are the three components that make it up. Visibility is closely tied to game requirements. So, for example, when calculating the visibility for the player in the game, the visibility is calculated based on the lighting on the floor near the feet of the player. And this is, again, because of the poor sense of physicality in a first-person game. By using his feet, it gives him a clear, objective position to use to understand his present state and anticipate his future safety. So our third AI, the player has hidden a body close to the wall in the shadow, in the pool of shadow there. This third AI has a sense link to that body, which is of low awareness because it's in the dark, it's definitely not moving, and it's close to the wall. And it's considered a first-hand sight link. Okay, jumping over to view cones. Unlike the Half-Life example, the Thief AI is built on a system of multiple ordered three-dimensional view cones that consist of an XY angle and a Z angle, where each view cone is configurable in its acuity, either its acuity on the whole or its acuity to any of the axes of visibility, movement, or exposure, or light. Furthermore, they can be configured and enabled and disabled based on the alertness state of the AI. And these view cones are oriented according to the head position of the AI. So as the skeletal system moves the body around, the view cones move with the position of the head. So when going to probe to see if the AI senses an object, the AI picks the first qualifying view cone in the ordered set for calculations. And that view cone produces a constant output regardless of the position of the entity in that view cone. So, for example, object A in this example is considered to be in view cone 3. Objects B and C are both considered to be in view cone 1. And if objects B and C were to have the same visibility values, they would be presumed to produce the same outputs from the function that governs the awareness function that governs cone 1. So visibility and the cone properties go into a look function. And the look function contains heuristics which generate a discrete awareness value. Now, as I mentioned, the owner's state, his mode, whether he's in combat or how agitated he is, can be used to affect how each cone performs. Now, the reason for having so many cones is to express the idea of peripheral versus direct vision along the same Z plane as the eyes, or above and below, or to get across low light vision. Furthermore, the way the system is configured is primarily through enumerated controls and not through a lot of numbers. The numbers are internal to it, but exposed are enumerations. Now, one interesting case in this diagram is cone 5. And this is sort of a good example of using the lower level system to achieve a higher level goal. Cone 5 is oriented out the back of the AI's head. Furthermore, it's been tuned to be sensitive to the movement field of acuity and to ignore light and exposure. And what this achieves is the sort of spidey sense that someone is right behind you, even though you haven't made any noise and they haven't touched you. Okay, I wanted to go a little bit into the pipeline. Pardon me. The system is designed as a series of components. Each of the components takes a well-defined set of data and outputs a still more limited, well-defined set of data. And each of these components can be individually scaled based on the game design. Furthermore, all the layers can be scaled down to virtually nothing, which almost achieves you the first-person shooter senses. The final output is, for a given object of interest to the AI in the world, a single discrete awareness value. And the heuristics of the system are essentially a black box controlled by the AI programmer and other programmers who understood the system. Now, by making it a black box, this raises the question of, how is this system tuned and how much did the designers participate? In this system, the programmers did most of the fine-tuning. This was because in order to tune the system, you really needed to understand what was inside the black box to actually change the way it behaved. Furthermore, you needed to be empowered, if necessary, to go in and just change the black box. This required lots of iterations, countless hours of iterations of play and experimentation, and then changing the system, and then play and experimentation and changing the system. This was done both by me and by Doug Church. Doug a little later in the project. The other thing about this is that if the outer systems that are providing information that the system depends on change, it may require retuning the system. So, for example, when Thief 2 shipped, it shipped with an upgraded renderer, 16-bit renderer at the time, which changed the sorts of lighting outputs for the information for calculating lighting the AI was getting, and so the system had to be rebalanced. Moreover, the system is really tied to the behaviors the AIs are going to be exhibiting. So in particular, search patterns and head movements. If you had one set of motion captures that you were using and then you tuned the AI to get those cones the way you wanted them and get the sensitivities right, and then they went out and got new motion captures that changed what the scanning patterns were, it's quite possible that the numbers you had picked before aren't valid anymore. And so one of the important things that the system tried to achieve was to acknowledge that the retuning was going to happen and make sure that the problem of retuning was not understanding how the system was behaving as it was, but really just knowing what you need to do to make it be the way it wants to be. So that's where the stability of the system comes in. The designers were given much simpler controls that allowed them to achieve the game design things they needed to do without really having to worry too much about the actual balance, the very fine-tuning sort of stuff. It wasn't a good way for them to be spending their time. So here's the pipeline. I'm not really going to talk about this slide per se, other than to sort of note that the component design was, to the extent the system was successful at all, it was successful because of its separation of the pieces. By having multiple pieces, each of which had a very specific information contract with the other pieces, it allowed each piece to be scaled and modified according to the needs of the game without worrying about the whole system at the same time. Vision is, when the AI goes to see, it takes the position of the object being viewed, chooses a view cone, takes the view cone and puts it together with the visibility being derived out of the lighting and the movement and the exposure of the object. These are fed into the look function. The look function's job is to take all this sort of soft, often analog data and output a single awareness pulse. This pulse is like someone turning on a flashlight at a certain color. This pulse gets sent to a component which receives the pulse, and its job is to then process that and actually generate the sense link. Sound, like in Half-Life, is relatively simple. And this is because it leverages the sophisticated sound system in Thief. If you've ever played Thief, you probably know that sound is crucial to the game. And because of its importance, we designed a sound system that allowed us to tag sounds with fairly meaningful semantic data And these sounds are propagated through a simplified version of the 3D space. They actually bounce off walls and go around corners. They have the correct occlusion and attenuation, so that when a sound arrived to the AI, the sound system had already produced all this very interesting information about it. Furthermore, the AI, when it spoke, could attach information packets to the sound as it went through the world, which, when it arrives at the ears, could be interpreted later. So sounds typically generate awareness pulses to points in space or to specific objects. Furthermore, sound is also a conduit for sort of awareness-inducing pseudosounds, just as the example in Half-Life. So if the designer ever wanted to get an AI interested in a place in the world, he had the tools to generate a sort of false sound to draw the AI there. These are fed into a listen function, which likewise produces a single discrete pulse of awareness. So let's just return to this example. Here the AI that was also observing the dead body doesn't have line of sight to the player, and he's pretty far away. He's around the corner. But he can hear the player's activity because the player is getting ready to fight the first AI we saw. So in this case, the AI has a medium awareness to a point in space from whence he heard the sound of the player. And this is considered first-hand knowledge. If that wall wasn't there, because the player is fully exposed and he's upright and he's probably moving because he's getting ready to run away from the first guy, he would have a high-quality vision sense link. Now, these aren't exclusive. You can have a vision and sound sense link at the same time. And this is important for generating the right enunciations later from the speech system of the thief AI. So the look and listen functions are generating these discrete pulses that go to a pulse receiver. And the job of the pulse receiver is to resolve the two into one. And at this point, the system is entirely discrete. There's no floating point math at all. And the rules are very simple. Whether the look or the listen pulse, whichever one is of a higher awareness value, that's your awareness. However, you wouldn't want to just do this, because if you did, your AIs would constantly be going in and out of being aware and would be like instantly aware of what's going on. If the pulse is going up, the pulse goes through a ramp-up delay component. This component is just a function of the current state of the AI and the current awareness of the AI, and not the goal state of the pulse. And the job here is to introduce time delays so that the AI will not immediately go into the target awareness level. And this is how basically player forgiveness factors are built into the system, or reaction delays are built into the system, so that if the player happened to pop out from a corner and there's an AI there that he didn't know was there, and he pops back quickly, then he isn't penalized and immediately hunted down and killed. If the pulse is going down, then it goes through somewhat of a capacitor that cools. When I go back to the first one, the other thing is, when you're going up, you never go through all the intermediate states. As soon as you pass your ramp-up delay, you go right to the goal state, because you don't want guys slowly becoming aware of the player. When you're moving down, the information goes through a sort of a capacitor that gradually lets the awareness from, let's say, high through medium down to low to very low, rather than having it drop really quickly. And this is, again, so you don't have guys completely forgetting you as soon as you go around the corner. The other responsibility of this system is if the player is no longer being seen, the AI is given a short degree of free sensory knowledge about the position of the player. And this is basically to achieve the appearance of deduction. I could have built a system that looked at the vector of where the player was going when he went around the corner and tried to figure out where he went, or I could just give the AI a second and a half of free knowledge and get the same effect as far as the player was concerned. And so it also does that. Finally, the the sense link is generated. This sense link contains all the data that the game needs to do something about it, and is picked up by the decision machine later. And I just talked about this slide. I apologize. Okay. The other important thing is that sense links, the way the system was designed, could also be, there are other ways to generate them besides the senses. So, for example, if the designer wanted to in some sense script something so that the alarm went off and the alarm went up and information cascaded through the level that where the player was, then he could just generate sense links to the player, which would have the effect of having the AIs go off and do what they would normally do if they saw the player. Okay. So I want to talk about some of the problems that a system like this presents. When the system was built, it was built for a game that was a single-player game with a software renderer. And the important thing here is this meant that all the authoritative information about the player or an object in the world or a special effect or anything was there at any moment to be used by the AI. But in a client-server, hardware-only rendering sort of environment, this might not be true. So it's important to note that a system like this is going to place very specific demands on the other systems in the game. Furthermore, it can be pretty CPU intensive. Now it's scalable, but even so, anytime you're spending doing this, you're not spending pathing or doing tactical analysis or other sorts of decision processes. Finally, it is a tuning commitment. If you're going to go for a system that isn't binary, it takes time to get the right feel, and you have to sort of schedule for that. Now, the benefit of this system is that it serves up distilled information to the higher level state machine in sort of a regular format and from a central location. This makes it a perfect place for expressing pre-conscious behaviors, or sort of the pseudo-sound example, perhaps other kinds of gameplay examples. Probably most importantly, I found it allowed us to generate, for the most part, varied and subtle behaviors to both enemies and companion AIs without adding a lot of complexity to the core decision machine. And it meant that not all programmers had to understand the system to get the sort of effects that they wanted out of the AI. So for further exploration, I recommend you look at the Half-Life SDK, which is available freely if you own Half-Life. And I also recommend checking out the tools that can be found on the Thief and Thief 2 CDs and at thiefthecircle.com. And I would like to apologize for rushing through the talk, and I'm sure I've forgotten something, so I encourage questions. But before I do, I'd like to just thank the people who helped me work through getting this distilled into less than a 2-hour talk and down to a 45-minute talk. Are there any questions? Yes?
You have all this cool information in the sense links. Can you maybe talk a little bit about what sort of analysis you did on that to generate behaviors from it, and how you maybe wrote the script, gave the designers to analyze all these different sense links and use them in scripts?
Sure. So the question is, the sense links, have all this data that's been generated by the sensory system. What was done with it, and what could the designers do with it? Well, from a high level, what was done with it was it answered most of the questions that in either the tactical or just other parts of the AI, the searching patterns needed, without them doing any calculations at all. So a lot of the behaviors in the AI needed these sense links because it provided them with the information they needed. For example, where is the player? When was the last time I saw the player? What direction was he moving? Did I have line of sight? Did I hear him? Did I see him? In terms of how this got manifest in the game, besides the sort of free knowledge cheating that I mentioned later, you could take the example of how was the tag that said whether it was a sound, a heard thing or a vision thing. The AI thief had a speech system for it that allowed the AI to aggregate a bunch of tags and combine those tags with a core sort of thought concept, pass that through a database of a sound selection database, and then produce an enunciation that was consistent with what it wants to say. So, for example, if I had a sense link to you and I heard your question, but my eyes were closed, and I'm up on this podium, the sense link, by storing your position and storing that was a sound, will allow me to say, "There he is down there," as a simple example.
So is it mainly used for, like, the more complicated information was mainly used for speech type stuff?
No, it was used for tactical stuff as well. One thing I forgot to mention is that there are certain things that kind of don't really go through this system in terms of how it collects data, but use the system to communicate to the AI. So, for example, when you fire an arrow, it gets immediately put in as a sense link because it's a fast-moving object that's just too fast for the system to detect. Or the designers had the ability to place objects in the world that aren't rendered but are being sensed by the AI. So, for example, this is how you could achieve the effect of the AI noticing that something was missing. Like, this player stole the chalice, and now he starts looking for this thing positioned in space, which is how the designers use it. Yes?
Two really simple questions. One is, with the links, was an AI storing linked links to represent history, or was it updating one?
So the question is, was a sense link a singular thing, or was it a history of the sensing? It was basically a steady. It was this current state without a lot of history, except there was some timing information in there. And the way it was stored was the dark engine on which Thief was built had this sort of relational object property system that Marc LeBlanc built for us that allowed you to store relational data and expose it to the designer. And if any objects either end of the relational link went away, it would clean up the data for you. And so that's how it was stored. So the AI didn't actually hold the data. Any other question? Yes.
You talk about when you have a ramp-up delay, so the player jumps out in front of the AI and then jumps back. The AI won't notice him. What causes it to stop continuing the ramp-up? Because it seems like otherwise, if he jumps out, there'll be a delay, but he will immediately go to awareness, even though he's hitting you.
Let me see if I understand the question. So if the question is, if the player jumps out and there's an awareness delay, what keeps him from continuing upward, even though the player has jumped back behind the corner, correct?
Right.
Well, that's because the way that works is that the sensory system outputs instantaneous pulses of awareness. And so if the player becomes hidden, those pulses are no longer being generated. And so the goal state is no longer high, for example. So the reason he doesn't keep ramping up is because there's no more information coming through. Because it's not actually ramping up. It's just saying, I'm not going to ramp for 1 second, or whatever the time actually was. I don't know if that answers the question. Yes?
So, how does sense links degrade, or recalculated every so number of frames, or what happens to that?
So the question is, after a sense link has been generated, what happens to it? How frequently are they updated, and how do they degrade? Well, the degrade, I'll start with that, it's sort of the flip side of the answer to the previous question. Because the output of the deeper system is just instantaneous pulses of awareness, they just degrade through this little capacitor that's just had been lit up to a certain amount and then just starts cooling down. And that cool down is a function of the kind of AI you are and the state you're in. So if you're in combat, you really don't cool down very much, because you don't want guys like hacking with their swords and then you go around the corner and they just kind of relax and say, "Oh, where'd he go?" Not that didn't happen in the game. The other question was what happens to them afterwards. I totally forget now what the other question was.
So, yeah, like, if you generate a sense like this process of degrading, does the AI then have that information until?
Yes. As it's degrading, the sense link exists until the AI decides there's just no more reason. In fact, in the game, sense links could exist dormant for a pretty long period of time after the AI had stopped sensing, because there was information there that I wanted to. It was cheaper to keep the information, to spend the memory to keep the information than to recalculate it later. And how is it scaled? The frequency of update was scaled. The AIs had like 5 levels of sort of activity, depending on where they were in the level relative to the player and what their job in the game was. Because at any time you might have 15 of them walking around trying to on their patrols. So it was scaled basically the frequency of update, and the fidelity of the update was scaled based on the internal state of the AI. Yes.
On a related note, then, of course, the player's on the other side of the map from a particular AI. You're not going to bother to check because there's just no chance of detection. So why would spend the
Check for the player.
Check for the player.
Yes.
On the complete other side of that, if there is a direct conflict happening between an AI and a player, let's face it, you don't need to spend the overhead to see if you still see him if he's beating you upside the head with a baseball bat. Is there a time when you just bought to switch off the sensory system because there is an obvious direct conflict between the player and the AI?
Okay, so the question is, like, let's say you're in the middle of engaging with the player, and would you basically go to the simple first-person shooter line-of-sight test and nothing else, since you're already in that state? It's kind of a tricky question. In the case of visibility, which is where a fair amount of the work of the system went, the answer is no, because the visibility is something that's actually a shared property of the viewed object, shared amongst all the AIs. So that had to continue to be calculated, regardless of any given AI's disposition to the player, for example. In case of the combat, I don't recall really toning it down that much if you were in combat. And I probably didn't. But that's because if you got into combat, usually you either ran away, in which case you needed to revert to the old thing, and I probably needed the information that had been there when you're standing there, or you got your ass kicked and the game ended. Probably if you were doing a fighting game where like you were in that state for a long time, you probably wouldn't take that approach. Yes.
You talk about visibility. Is there an analogous audibility? So, like, say, if there's a loud noise going on, you can do something quiet and it won't be noticed because of the noise?
So, all right. So the question is, was there some analogous thing to audibility, to visibility in terms of audibility, so that the player could have cover from loud noises? So if you're walking by machinery, even though you're walking on, a Dance Dance Revolution board, you're not going to make noise. And the answer is, in Thief 1, that wasn't the case, and in Thief 2, we modeled some of that, I believe, but it was not modeled using the sensory system. It was modeled by other means. That's my recollection. Yes?
The sense links, was there ever more than one, or is it pretty much like one? Did the AIs have sense links to other AIs at the same time as the other sense links, or is it totally player-centric?
Sure. So the question is, was there one sense link or many sense links? And if I was good at PowerPoint, I could get quickly back to the slide. The answer is that AIs had any number of sense links, but its relationship to any given point in space, or any given other entity in the world, there was just one. And AIs had sense links to their companions on their squad. They had sense links to their enemies. They had sense links to bodies in the world, to things, gameplay things, all of which had to be updated and stored.
Just to add to that, how did you manage the priority system on that, and was it ever, can you talk about that at all?
Sure. The question is, how do I manage the priority of all that? It's kind of outside the scope of this talk, but there was a system that then would take the aggregation of all the sense links and make a decision about what the agitation level of the player should be and who the AI should be targeting or what his activity should be. And mostly that manifests itself as the alertness level. Yes?
I apologize if I missed it in the talk, but you mentioned the second-hand and first-hand flag.
Yes.
How is that used in the game?
Okay, so the question is, I mentioned that I had second and first hand and then an absence set of flags for the sense links, and how is that used in the game? The primary use for that in the game, some of it was verbalization, although that was only a few cases where that happened. The primary use of that was to control the information propagation. The AIs didn't actually share knowledge behind the scenes unless I really needed to obtain an effect, so that the information they had was derived by either seeing the activity of the other AIs or by hearing their verbalizations. And so I could use the first and second hand knowledge, and there was also stuff stored about how much a sense link had been propagated to prevent the entire level from cascading into alarm. So that was like an after system, outside system. Yes? I'm sorry, I can't actually hear you. Can you speak up?
I remember from playing the first Thief game on the easier settings, the guards would actually walk into you and not notice you were there if you were still in a dark area. Was that actually a deliberate thing that collision detection wouldn't be part of the senses, or was that just done?
Sure. So the question is that in the game, you could get into dark corners, and AIs would come right up to you, and they would bump into you and not seem to notice you. And the question is, was that deliberate, or was that a bug, or what have you? I'd like to say it was a bug because it really annoyed a lot of people. But in point of fact, it was a deliberate choice because we wanted the player to, if he had achieved a point of complete safety, to be in that safety. Now, there were cases where if you bumped into an AI, it would generate sense links. Like even if that back view cone hadn't worked, the player who bumps into the back of an AI will generate a sense link to the point in space behind him, and he's supposed to. In that case, sense links that show up too fast, this information about like how long it took for that sense link to show up could be used to generate surprise. So if you bump into the back, you'd have this like sense link that came out of nowhere, and that's why he would spin around and say, "Oh my God." Any more questions? Yes.
You have a sense link that was created from a sound event, and the sense link has some directionality component to it. But if you have sounds that are potentially bouncing off walls and obstacles, how do you guys handle that?
So we have sounds that are potentially bouncing off walls and obstacles, and so the sound comes from an arbitrary point in space, an arbitrary direction, correct? Is that the question? Yes. So what do we do about that? Well, usually we took advantage of the fact that the simplified version of the world that the sound was propagated through often left us with a point that happened to be, about, in the way the propagation model worked, about the middle of the doorway, around the corner where the sound was coming from. Occasionally, a sound would come. The two problems that were more complicated. Occasionally, a sound would come from two positions in space, say a door and a window. And in the case of the window, it's something that the AI can't really do anything about because, he's planted on the ground. Basically, the way we handled that was the pathfinding system in Thief was this auto-generated navigation mesh that came out of the world representation directly, and it was impossible to not be in it. And because of information gathered while it was being constructed, even no matter where a point was, I could always. The pathfinding system allowed me to develop queries that got me back to a reasonable point for the AI to be thinking about. Say back, if it was in the window, I could pull the point back in and then down to the floor closer to where the AI could actually do something about it. Although it still retained the fact that it was from up high as opposed to down low. Yes?
With this sort of complex sound propagation model, how do you provide feedback to the players that they were in a position that they couldn't make a sound because it wasn't directly at their line of sight?
So given this complex model, how do we communicate to the player that they can't make a sound, even though the player can't see the AIs? And that was a big part of the game design, because this is where the senses of the player come in. The game required that the AIs constantly be sort of announcing what their state was and what their intentionality was. And furthermore, even if you saw them, we had these goofy-looking, but for gameplay purposes, appropriate, very exaggerated motion captures that sort of said, "I'm searching for you, and I'm looking in that direction," and they would make verbalizations to the effect of how certain they were. And this is where, like, the example of scent is one that was suggested to me by Dave Kalina, who's working on Thief 3, and I've also worked on Splinter Cell, where I haven't had time to play Splinter Cell, I apologize. But he was saying it was very difficult for the case of dogs, to get that kind of feedback about why is the dog finding me, even though I'm where I am, because the company that made the sort of smell-o-vision for games went out of business. I hope none of them are here. Yes?
With something like footstep sounds from the player, would you create sense links for each footstep sound, or would you call them out?
Okay, so the question is for footstep sounds, or let's say, I'll generalize that to other sounds emanating from objects in the world. Were sense links generated for each sound at a position in space where the footstep took place, or was it generated for the object? And in that case, the sound sense link, the hearing sense link, was generated for the object that made the sound. And the decision to do that or another was not like a heuristic. It was just hard-coded, like, it's the player footsteps. Come on, it's going to be coming from the player. Yes?
When you hear an non-player character is announced that he's easy or is that the same sort of sound that's also communicating to the other non-player?
Okay. So the question is, when the player hears the AI announce that he's been seen, or that he thinks he's been seen, or that he heard something, is that the same thing that is triggering the other AIs to inherit sense links? And the answer is yes. And in fact, for better or for worse, if an AI did not choose to announce, then the other AIs would not actually get that information. Although they might observe them entering a mode of searching and begin to get a little concerned using a sense link. I am apparently out of time. I thank you for coming, and please fill out our lovely yellow things.